So in this video we'll discuss about electric dipole, dipole moment and electric field due to dipole on its axis on its equatorial line, and also if a electric dipole is placed in an external electric field, what happens, what is the torque acting on it. All these things we'll discuss in this video. A charge of negative polarity minus q and another charge plus q, if you take the system of these two charges, it forms a dipole. So the length of the dipole generally we take as 2L. And dipole moment, what is dipole moment also? You see, the dipole moment we represent with the P. The direction of dipole moment is from minus q to plus q, negative charge to positive charge. So here a dipole is nothing but electric dipole is system of two equal and opposite, let me write here, system of two equal and opposite point charges separated by a very small and finite distance. So dipole we can define as, we can understand the dipole as, it is a system of two equal, that is magnitude of this charge minus q what we are taking and plus q, the magnitude is same. The system of two equal and opposite point charge, that is polarities opposite, different polarities, and they are separated by a distance, a small finite distance. So that distance we take as 2L. Okay, that we can define as a dipole. The dipole moment is a vector concept. Let me write here, dipole moment. This is a vector, and if you want to define it, it is if you want to write formula, p bar equal to product of magnitude of one of the charge and separation between two charges. You can write as 2LQ. So the dipole moment P bar we can write as 2LQ. What is the direction of P bar is? The direction is from negative Q to positive Q. The direction from minus Q to plus Q. That is the direction of the dipole moment of an given electric dipole. Now we'll see electric field strength due to a dipole. The case one is on the axis of the dipole. What is the axis? The line that is passing through the along the length of the dipole. That is the axis of the dipole. So let us take at this point at a distance r from the plus q, say the length of the dipole is 12. If you take center as the reference one, the center of the dipole, then this becomes L and this also L. So here at this point, the electric field due to plus q charges in the direction of the axis, that is positive x direction, you can write as E plus. This minus q, it attracts, so the direction of the electric field due to minus q is, we can write as E minus. Since this q is nearer to this point than minus q, the positive charge is nearer to this point than the minus q, therefore here the net electric field, that means what, here E plus, magnitude of E plus will be greater than E minus. So the net electric field will be in the direction of the, along the direction of the axis, or we can say simply in the direction of the dipole moment. When you consider if you want to know the direction of the electric field along the axis of the dipole, it is in the direction of the dipole moment. So let us take one more here at the left side also, we'll see it what happens. And either side of dipole you take on the axis of the dipole, the phenomena is same. See here, what is happening here, this minus q attracts it, that is the electric field due to minus q we can write as E minus, and electric field due to positive charges, repulsion, so you can write in this direction. But since the minus q is nearer to this point, and you take some distance or something like, okay, nearer to that, here the E minus is greater than E plus. Therefore, what is the E net value, Nana? E net is what? The net electric field is in the direction of the E minus. So this is the direction. So either point you take, the electric field direction is in the direction of the dipole moment. So what if I take in between? Somewhere here if I take a charge, not at exactly middle, this plus q repels, minus q attracts. Plus q repels, minus q attracts. See here, at any point you take, any point between the two charges, this is the direction. Both the directions, both the electric fields are in the same direction. So in between the electric field direction is plus q to minus q. But in general, we take the dipole as a system. It is a small, the length between separation between the dipole is very small, 5 nits. So between the two dipoles, the effect or taking the things we don't do. If any numerical is asked, you can consider that one. So here point is either side of the dipole, the direction of electric field is in the direction of dipole moment p bar. So the dipole, if you take dipole, this is minus q plus q, the length is 2l, and on the axis of the dipole at point P, let us calculate what is the net electric field. The point P from the center of the dipole, say at a distance r. So because the length of the dipole is 2l, you can write this part is L, this part is L. And due to plus q charge, say here electric field intensity is E plus, due to minus q charge, E minus. Already we discussed in the basic concept. So what is the E plus will write? What is the net electric field? E bar is equal to E plus bar plus E minus bar. Since two directions are mutually opposite in direction, that is the angle is 180 degrees, you can apply parallelogram law of vectors. Then the magnitude of E bar you can write as E plus minus E minus. Okay. So here E plus equation will write K is 1 by 4 pi epsilon naught here. K into, I am taking the system of this dipole system in the air medium or vacuum. Okay, so E plus is equal to K into the magnitude of the charge is Q divided by what is the separation, what is the distance here from here to here, it is R, but we need from this charge, from plus Q charge. So R minus L whole square. So that becomes R minus L. This separation becomes R minus L. Okay, right. Let us write E plus also. E minus. What is E minus? That is from minus Q. K into Q by R plus, right, R plus L whole square. So final equation we can write here, you just substitute the values and you can do it, take it as homework. On an axis of the dipole, the E we can write as E, because E1 minus, that is E plus minus E minus. Final equation, what will you get, Nana? What is the final equation we get? So the final equation we obtain is K into 2pr by R square minus L square whole square. So here K is 1 by 4 pi epsilon naught. If you place the system of dipole in a medium, then any medium, that medium EM equal to, that is K, here K, in place of K, in place of 1 by 4 pi epsilon naught, we write 1 by 4 pi epsilon naught epsilon R. So simply you can divide with dielectric constant or relative permittivity epsilon R. A simple phenomenon. Okay, where epsilon R is dielectric constant of medium. Dielectric constant or a relative permittivity. Relative permittivity of medium. Clear? So here in this point, for example, comparative to the distance of that particular point on the axis of the dipole, or if the dipole length is very small, see here this L, what is L? Half of the length of the dipole. Generally the separation, the length of the dipole is very finite, very small, and if you compare that with R, if that length is very small, that is if R is greater than L, what is R? That point on the axis of the dipole greater than, we can neglect that L square in the equation. So electric field on the axis of the coil, the electric field on the axis of the dipole, we can write as K into 2pr divided by R square over square, that is R power 4. So K into 2p by R cube. The final very important point you remember, the direction of the electric field on the axis of the dipole, on the axis of the dipole is in the direction of the dipole moment p bar. This point you remember. In the next video we'll see what is the electric field on the equatorial line of the dipole.